Hello everybody, I welcome you all to my fourth lecture on time response of control system. My name is Kiran and I am working as an assistant professor in the department of EEE Anits. In my first lecture I discussed what is time response, what is steady state as well as transient state responses. What are the various standard test inputs, that is step input, ramp input and parabolic inputs. Also defined what is steady state error and derived the expression for steady state error. We also seen the various factors on which the steady state error depends and their effects. In the second lecture, we have discussed tutorials based on various error coefficients Kp, Kv and Ka and correspondingly their steady state errors but for step, ramp and parabolic inputs. In my third lecture, we have derived the expression for time response of first order system with unit step, ramp and parabolic inputs. We have also derived the time response of second order control system with unit step input in 4 cases, that is undamped, underdamped, overdamped and critically damped systems. In today's lecture, we are going to see what are the various time domain specifications, or in other words transient response specifications. We are going to derive the expressions also of all these time domain specifications. The first time domain specification is delay time, denoted by TD, and it is defined as the time required for the response to reach 50% of its final value in the first attempt, and mathematically it is given as TD is 1 plus 0.7 into zeta by omega n. The second time domain specification is rise time. It is denoted by TR and it is defined as time required for the response to rise from 10% to 90% of its final value in case of overdamped and 0 to 100% of the final value in case of underdamped. It is mathematically given as pi minus theta divided by omega d. The third time domain specification is peak time. It is denoted by TP. It is defined as the time required for the response to reach its peak value, and mathematically it is given as TP is pi divided by omega d or pi divided by omega n into root over 1 minus zeta square. The fourth time domain specification is peak overshoot, denoted by MP, and it is defined as the largest error between reference input and output during transient period, and mathematically it is given as percentage peak overshoot is e power minus pi zeta by root over 1 minus zeta square into 100. And the fifth and last time domain specification is settling time, denoted by TS. It is defined as the time required for the response to decrease and stay within the specified percentage of its final value. And its expression is given as 4 by zeta omega n if plus or minus 2 tolerance band is allowed. If it is 5% tolerance band, then its expression is given as 3 by zeta omega n. So now we are going to define, we have finished defining all the time domain specifications. So now it's time to derive the following time domain specifications, that is peak time TP, rise time TR, peak overshoot MP or percentage MP, and settling time TS. The first one, we are going to derive the peak time TP. So we know the time response of second order underdamped system is given by, which we have seen in our last lecture. So C of t is equal to 1 minus e power minus zeta omega n into t divided by root over 1 minus zeta square into sine of omega dt plus theta. Please remember that all the time domain specifications are valid only if the system is second order underdamped system. For remaining type of systems, these time domain specifications are not valid. Okay, so we can derive the expression of peak time by obtaining the first derivative of the output response and replacing t by tp, that is peak time, and equating it to 0. So first we'll differentiate the above expression with respect to time. So we know the formula for u in derivative of u into v, isn't it? So applying that formula, so if I consider this as u and this as v, so if I apply derivative of u into v, so the derivative of first term will give me e power minus zeta omega n into t into minus zeta omega n, and v it is as it is, minus the derivative of this second term will give me cos omega dt plus theta into omega into the first term, it is as it is, and this I am equating it to 0. So now we know that omega d is omega n into root over 1 minus zeta square, isn't it? So here omega d I'll replace by omega n into root over 1 minus zeta square. Okay, so both sides e power minus zeta omega n will get cancelled, and both sides root of 1 minus zeta square will get cancelled, as well as omega n will get cancelled on both sides, isn't it? So on left half the equation I'll be left with zeta into sine omega dt plus theta, and on the right half of the equation I'll be left with root over 1 minus zeta square into cos omega dt plus theta. Okay. So this I can write as tan omega dt plus theta is nothing but root over 1 minus zeta square by zeta. But we all know that this expression is nothing but tan theta, isn't it? So now from trigonometric analysis we know that tan n pi plus theta is equal to tan theta. So if I compare this with the previous expression, I can conclude that omega dt is equal to n into pi, where n is 1, 2, 3. Since peak time is the time required for first peak overshoot, here we will consider n value as 1. So that will give me omega dt is equal to pi. So in place of t I will substitute the peak time tp, and that will give me the expression of peak time tp as pi by omega d, or pi by omega n into root over 1 minus zeta square. The second derivation is the rise time. We all know that the time response of second order underdamped system is given by c of t is 1 minus e power minus zeta omega n into t divided by root over 1 minus zeta square into sine omega dt plus theta. Okay, since it is rise time, it is the time required for this response to reach 100% of its final value. So I am equating the response to 1, since 1 is considered as the final steady state value, and replacing t by tr, that is rise time. So that will cancel these two and will give me the expression of minus e power minus zeta omega n tr by root over 1 minus zeta square into sine omega d tr plus theta to be 0. And this equation will only be satisfied if this term, that is sine omega d tr plus theta, is equal to 0. Because there is no way that this expression, that is the first part, will become 0, because zeta is never 0, omega n is never 0. So this equation will only be satisfied if the later part of that sine term, that is sine omega dtr plus theta, is equal to 0. So trigonometrically this is true if omega dtr plus theta is equal to n into pi. so n is equal to 1. So that will give me the expression of rise time to be pi minus theta by omega d, where omega d is omega n into root over 1 minus zeta square. The third derivation is maximum peak overshoot MP. We know the standard second order underdamped system expression. C of t is 1 minus e power minus zeta omega n t by root over 1 minus zeta square into sine omega dt plus theta. So here maximum peak overshoot MP is nothing but the difference between the steady state value and the peak value, isn't it? So I'll take the difference of these two. So substituting t in place of t, I'll substitute TP. I'll consider TP. This will cancel out these two terms, which eventually will give me the value of MP as minus e power minus zeta omega n into TP by root over 1 minus zeta square into sine omega d TP plus theta. Okay, but we know the expression for TP. Peak time is pi by omega d, isn't it? So I'll substitute here in place of TP as pi by omega d. So in place of TP, I'll get sine pi plus theta. Okay, so we know sine 90 plus theta is minus sine theta. So that will lead me to the expression of MP as e power minus zeta omega n into TP by root over 1 minus zeta square into sine theta. So we all know the expression for tan theta, isn't it? It is root over 1 minus zeta square by zeta. Okay, if we place this in a right angle triangle, that will give me the expression of sine theta to be root over 1 minus zeta square. This I will replace in this above expression. That will cancel out the term root over 1 minus zeta square, which is already present in the denominator. Therefore MP value will be e power minus zeta omega n into TP. Again here TP is nothing but pi by omega d. So I'll substitute that, and omega d is eventually omega n into root over 1 minus zeta square. That will cancel out the values of omega n, and ultimately the percentage peak overshoot will be the expression e power minus pi zeta divided by root over 1 minus zeta square into 100. And the last derivation is the settling time. We know the time response of second order underdamped system. It is C of t is 1 minus e power minus zeta omega n into t divided by root over 1 minus zeta square into sine omega dt plus theta. Since it is settling time, let us assume that we are considering plus or minus 2 tolerance band, which will give me the time, settling time to be 98% of its final value. Okay, so 98%, I mean that the response C of t can be equated to 0.98 value. Okay, so and one more thing we need to keep in mind, that the transient part or the oscillatory part will not be present at the settling time. Okay, so here this part, that is sine omega dt plus theta, consists of transient or oscillatory part. Okay, so this term will not be there. We will neglect this term. So in order to derive the expression for settling time, we will only consider the exponential term, that is e power minus zeta omega n into t, and the remaining terms we will neglect. So that eventually will give me the expression C of t to be 1 minus e power minus zeta omega n into ts, isn't it? And this is equal to 98%. So that is why I have equated to 0.8 and replacing t by ts. Eventually the value of settling time will be applying natural logarithms on both sides, will give me the expression of settling time to be 4 by zeta omega n. So this concludes my today's lecture on time domain specifications. We have defined various time domain specifications, that is delay time, rise time, peak time, peak overshoot and settling time. We have also derived the expressions for rise time, peak overshoot as well as settling time. Thank you.